Okay, so hello everyone. I think it's time to start. Welcome to the IEEE ComSoc-SPS ISAC webinar series. And today we're gonna have Professor Liu Fan to give us a talk. So to start with, let me have an introduction about Professor Liu. So I think everyone should be familiar with him. So Professor Liu Fan is currently an assistant professor of the Department of Electronic and Electrical Engineering, Southern University of Science and Technology, China. He received the PhD and bachelor degrees from Beijing Institute of Technology, Beijing, China. He has previously held academic positions in the University College London, UK, first as a visiting researcher and then as a Marie Curie Research Fellow. His research interests includes the general area of signal processing and wireless communications, and particularly in the areas of integrated sensing and communication. He is the founding academic chair of the IEEE ComSoc ISAC and associate editor for the IEEE Communications Letter and the IEEE Open Journal of Signal Processing, and the guest editor of the IEEE JSAC and the IEEE Wireless Communications. He was also an organizer and co-chair for numerous workshops and special sessions in flagship IEEE ACM conferences, including ICC GlobalCom, MobiCom, ICASP, and SPOC. He is a TPC co-chair of the second and the third IEEE Joint Communication and Sensing Symposium. He was listed in the world's top 2% scientists by Stanford University, and he was also the recipient of IEEE Signal Processing Society Young Author Best Paper Award and the Best PhD Thesis Award of Chinese Institute of Electronics. Okay, so before we also have some Q&A rules. So please keep muted during the seminar for all the audiences. And notice that please do not allot it on your screen because everyone can see your annotation. Also, please type your questions and send them to me or other co-hosts, okay? And we will connect questions from both audiences from Zoom and also some other offsite live broadcasting. And during the Q&A session, we will choose 3 to 5 questions to ask the speaker, okay? So that's all for the introduction. Let us welcome Professor Liu. So Fan, the stage is yours.
Okay, many thanks, Jie, for your nice introduction. And let me first share my screen. So can everyone see the screen now?
Yes.
Okay, so thank you very much for this opportunity to present in this webinar series. So actually, we have been organizing this ISAC webinar series for a very long time, and this is the first time that I'm presenting to you. Okay, so today I'm going to talk about our recent research on the fundamental trade-off of integrated sensing and communication on the Gaussian channels. So here are my collaborators for this series of work, including Professor Yifeng Xiong, Professor Kai Wan, Professor Yuan Haocui, Professor Wei Jieyuan, Dr. Tony Xiaohan, and Professor Joseph Kerr. Okay. And as always, we have a bit of background on ISAC for people who are not very familiar with this topic. So we see that ISAC refers to the design paradigm and corresponding enabling technology, while sensing and communication systems are integrated to efficiently utilize the resources and to pursue mutual benefits between them. And the motivation for the ISAC is actually twofold. One is from the technological aspect. We see that sensing and communication, they are going to higher bands, large antenna arrays, and also miniaturizations. And we see that sensing and communication converge in hardware architecture, channel characteristics, and signal processing at millimeter wave and terahertz band. And there are lots of emerging beyond 5G and 6G and IoT applications require integrated sensing and communication designs. And also from the commercial aspect, we see that sensing is now well recognized by the communication industry as a basic service and a native capability of the next generation wireless networks, such as Wi-Fi 7, beyond 5G and 6G. And there are lots of novel civilian radio sensors like Solly from the Google face challenges from the spectrum regulators worldwide. So there's a there's an approach to there's a desire to exploit the communication spectrum for sensing. Also, there are more and more severe spectrum congestion problems. So these are the motivations for why we investigating this integrated sensing and communication technology. Okay, so let's first look at the performance metrics for sensing and communication. Since today we are going to talk about the fundamental trade-off between the performance of sensing and communication. So we can see that the communication is typically measured from two aspects. One is efficiency, the other is reliability. So efficiency is to evaluate how much information is successfully communicated from the transmitter to the receiver given the limited resources. And the reliability, of course, is to measure the ability of a communication system to reduce or correct the erroneous symbols in the presence of noise and interference. And accordingly, we have for efficiency and reliability, we have different performance metrics for communication systems. For example, we have spectral efficiency, we have energy efficiency, we have bit error rate, symbol error rate, or frame error rate for the robustness or reliability aspect. So that is for the communication system. But for the sensing system, things become a little bit different because we typically do not measure sensing performance from the efficiency aspect. So you can see actually all these sensing metrics, they are divided, they're dependent on specific sensing tasks. So what kind of sensing tasks do we have here? We have detection, which is to make decisions on the state of a target, and estimation, which is to extract useful parameters of the sensed object, like the range, Doppler, and angle. Okay, so recognition, which is to know what the sensed object is. So you can see that almost all the metrics for these different sensing tasks, they are reliability metrics or robustness metrics. So for example, we have detection probability, we have mean squared error for estimation, we have also the lower bound of a mean squared error, which is parameter bound, and we have recognition accuracy. So all these metrics, they're trying to tell you how reliable your sensed result is. So what is the error of your sensed results, and what is the probability that you detect a target? Okay, so you can see that for sensing, we have different metrics in terms of different tasks, and most of them are reliability metrics. And today our particular focus would be on this. Sorry, let me use the. Oh, sorry. Okay, I just used my. Okay, so so today our particular focus would be on this parameter bound. So which is a measure of how good an unbiased estimator is. So an unbiased estimator is the estimator that yields the estimate of a parameter which has an expected value that is equivalent to the ground truth. So that is a definition of unbiased estimator. So more accurately, CRB is the lower bound for the variance of all the unbiased estimators. And it is also the inverse of the phase information. So you can see that if we look at these likelihood functions, we can see that the phase information is actually to measure how sharp these likelihood functions are. So you can see if we have a very sharp likelihood function, then my estimation will be more accurate, right? So the general expression for the CRB is actually the inverse of the phase information matrix. So here, this is a phase information matrix, and it is the expectation of the second derivative of the, here I'm using the joint distribution of my observation y and my parameter eta. So if eta is random, then this becomes a Bayesian CRB, right? So we will have a prior information, prior phase information that contributes to the estimation. And if eta is deterministic, then this py eta is known as the likelihood function, and that will give you the normal CRB. So this is the inverse of the phase information, and this is the MSE matrix. So you have eta, which is a parameter to be estimated, and eta hat, which is estimation of that parameter. And the MSE matrix is larger than or equal to the inverse of the phase information matrix in a semi-definite sense. Okay, so this is the inequality in a semi-definite sense. Okay, this is the Cramer bounded definition. And what we are going to discuss today is a very basic trade-off in ISAC system, which is a trade-off between CRB and communication rate. Okay, so here we are using CRB as the metric for the sensing performance. We do not use MSE because it is determined by the specific estimator. So this MSE depends on what kind of estimator you're using to estimate this eta. Okay, so to guarantee the universality, we're using this Cramer bound as the metric for sensing. And of course, for communication, we're using this communication rate. And here we can have different boundaries. So boundary A, you can see, which is a straight line, right? So linked to 2 points. One is the minimum CRB and one is maximum rate. So a straight line linked to each other. And in this case, we see that there's no performance gain in ISAC system because this boundary can be simply achieved by very simple time sharing performance, time sharing strategy. Or in other cases, we can achieve this using orthogonal resource allocation, or we can using a separated radar and communication systems. And in that case, we do not have performance gain over individual communication radar. And boundary B is the very idealized scenario while there's no trade-off between the communication and the sensing performance. Both functionalities achieve to their optimum. You can see that in this case, if my ISAC system works at this boundary, then I can have the minimum CRB, and in the meantime, I can have maximum rate. So that is perhaps the perfect scenario. And in this case, there's no trade-off. But in most cases, you can see that the boundary or the trade-off between the communication rate and the sensing performance is something like boundary C, okay? So it is something in between boundary A and boundary B. And there's, of course, trade-off between communication and the sensing systems. And compared to isolated systems, isolated radar and communication systems, we should have some sort of performance gain in ISAC systems. So why is that? So let's look at this problem from a resource allocation perspective. So we all know that we have different types of wireless resources. For example, we have resources in time domain, which is the time duration you allocate to different users or different, here we allocate time to different functionalities, sensing and communication. And we may have spectral resources like antennas, like beams, okay? Oh, sorry, the frequency resources, okay? And in the spatial division case, we have beams and antennas, and they are resources. And in this case, we can have orthogonal resources allocation. For example, I can use part of the time duration for communication and the other part for sensing. And here I can use part of the subcarriers for communication and the other half for the sensing. And here I can use part of the beams for communication, the other part for sensing. So in all these orthogonal resources allocation cases, you can see that communication and sensing, they will not interfere with each other, right? Because they are scheduled on different orthogonal resource domains. And you can see that this is apparently a very low efficient signaling strategy. So what about we're using a unified waveform? So a unified waveform is that we're using this all the resources. So all the resources, including time resources, frequency resources, and spatial resources, they are shared between communication and sensing. So we're using essentially the same signal to do both sensing and communication. But in any case, if in any resource allocation schemes, when the wireless resources, they are shared between sensing and communication functionalities, there will be naturally performance trade-off due to the contradictory design objectives for communication and sensing. So as we discussed here, we have different performance metrics for sensing and for communication. So that is why we'll have this kind of trade-off. So like in boundary C, this is a very typical Pareto optimal boundary for two objective functions, CRB and rate. So Pareto optimal means that when I improve CRB, I will have to sacrifice the rate, okay? So that means I'm achieving the Pareto optimal boundary of this optimization problem. So how is this trade-off determined? So what is the, so how can we determine the shape of these boundaries, okay? So that is a very important problem. How can we know whether my ISAC system is working at boundary C or boundary A or boundary B, okay? So I think that is a very fundamental question that we need to answer here. And we see that actually these trade-off boundaries, they are determined by the coupling strengths for ISAC channels, or more specifically, the coupling strengths between sensing and communication channels. So basically, for all the ISAC cases, we can consider three different cases. So weakly coupled, moderately coupled, and strongly coupled. Here, the coupling means the correlation between two channels. So we have a sensing channel, we have a communication channel. So what is weakly coupled? So if we look at this figure and we see that here the weakly coupled case has two channels, a sensing channel, which is to sense a target, which is a vehicle on the road, and a communication user, which might be a UAV in the air, right? So you can see that the beams will be well separated for these two objects. You can see in this case, we see the communication channel and the sensing channel, they are weakly correlated with each other. So, or even there's no correlation between them. So that is a weakly coupled case. And there's also moderately coupled case. So moderately coupled case means that we may have something like this. We are doing Wi-Fi sensing using communication signals. We have a Wi-Fi access point here, and we have a cell phone, let's see a communication user, and we are trying to use that, receive the communication signal to do, let's see, the hand gesture recognition using the reflected signal, right? So you can see for the communication, we have two paths in this case. One is the line of sight path, and the other is this reflection path, which is generated by our hand gesture. So you can see in this case, the sensing target is part of the communication channel, okay? And in this case, we see sensing and communication, they are moderately coupled with each other. And also there's a strongly coupled case. Well, we can have the sensing target, which is also a receiver, which is also a communication receiver for the ISAC signal, right? So that is also a very typical case, especially in the, let's see, the V2X network. So for example, I'm using this ISAC signal, I'm transmitting this ISAC signal from the base station to both detect a target and transmit information to this vehicle, right? So this vehicle is both a target and the communication receiver. So you can see we are using these three categories to categorize the coupling strength for the sensing communication channels in ISAC systems. So here we're trying to define what is the performance gain in ISAC. Okay, so here we see that the ISAC gain is closely related to the coupling strength between the communication and sensing channels, or more accurately, the communication sensing subspaces. Okay, so this can be illustrated in a very intuitive way like this. We have two subspaces. One is sensing subspace, and the other is communication subspace. They are determined by the channel characteristics. Okay, so this is a very abstract object, a mathematical object to describe the sensing communication channels. So we have sensing subspace, we have communication subspace, and they may have different correlation between them. So we may have weakly coupled case, we may have moderately coupled case, we may have strongly coupled case. And our ISAC signal is a vector spanned in these subspaces. So you can see if my communication and sensing subspaces, they are weakly coupled with each other, then these two subspaces will be orthogonal to each other. And the performance of sensing and communication will be determined by the projection of this ISAC signal onto these two subspaces, right? So you can see these projections are rather weak. And if there's a certain intersection angle between two subspaces, which is a moderately coupled case, then you can see the ISAC signal will generate larger projections on the two subspaces, which give you better performance for sensing communication. And in the best case, we have the strongly coupled case, while the sensing communication subspaces, they're fully aligned to each other. Then in this case, the signal power of the ISAC signal can be fully reused between sensing and communication. And that will exactly correspond to the case where we have no trade-off between sensing and communication. So this is a very simple example of this illustration. So we're considering a very typical beamforming problem, in which case we're optimizing this W, which is a beamforming vector in the base station, and we're detecting a target located at theta, and we're transmitting information also to a communication user, and we need that communication rate to be larger than R0. So both CRB and rate is determined by this beamforming vector at the base station. So if I'm doing this minimization problem, and then I can get a Pareto optimal boundary for CRB and rate. And these are the Pareto optimal boundaries in terms of the different correlation coefficients between communication and sensing channels. So from 0 to 1. So when the correlation is 0, that means the sensing subspace and the communication subspace, they are weakly coupled, then they are orthogonal to each other. And when rho equals to 1, then that means the two subspaces, they are strongly coupled with each other and they are fully aligned to each other. And in between this 1, 0 lies the moderately coupled case, which give you the trade-off curves like this, right? So that is how this coupling strength determine the performance gain. And of course, you can see the performance trade-off becomes better and better if I'm increasing this rho from 0 to 1, right? So that is why we see the ISAC gain is determined by the coupling strength between these two subspaces. Okay, so with that, we can actually summarize ISAC gain. So in our previous works, we have done lots of optimization on beamforming and waveform design for ISAC signals. And actually, most of these problems can be categorized as this kind of trade-off problems. And you can see that the performance gain is actually determined by your communication and sensing channels. So then there's a colleague, there's a friend of us, and he once said to us that you have done lots of research on ISAC, beamforming, on waveform design, and for those optimization problems, what you are doing is simply about how you are using a torch or a flashlight more efficiently, right? So you can see, if we look at these three figures, where it is as if that we're using this ISAC flashlight, right, to try to steer to the communication user and also the sensing objects, right? So this is why he said that this is simply a flashlight problem. Okay, so we see that while this is true, but this only reveals half of the picture, and we will see that another aspect of this ISAC torch also matters. Okay, so now we can enter into our technical details of today. So today, as suggested by our title, we'll consider the fundamental trade-off of ISAC systems in the Gaussian channel. So in particular, we're considering this so-called vector Gaussian system or vector Gaussian channel. Okay, so it looks like this. This is, I think everyone is very familiar with this, right? So we have here X, which is an ISAC signal, okay? And then we have ZC, ZS. So ZC, ZS are noise signals. And YC, YS are received communication signal and receive the sensing signal. And here HC, HS, they are communication channel and sensing channel, okay? And actually this kind of model can describe lots of ISAC systems. So for example, we can look at these two types of ISAC setting, which in this case is monostatic sensing, and in this case it is bistatic sensing. So we have in monostatic sensing, we have a ISAC transmitter, okay, and a sensing receiver. They are co-located with each other, just like a monostatic radar, and it transmits an ISAC signal both to a communication receiver and also to detect a target. So it will receive the reflection from the target, right, like this. So received by this sensing receiver, and also the communication receiver will receive the ISAC signal from the communication channel. So this is a monostatic sensing case. And we may also have this bistatic sensing case, in which case this sensing receiver can be well separated with the ISAC transmitter, but they can be linked with like say the optical fiber, which is a wild link. Okay, this can this might be not necessarily be a wireless link. Okay, so this corresponds to a structure called bistatic radar. And again, we're transmitting an ISAC signal to the communication receiver and also to detect target and received by the sensing receiver. So we use this model to describe both ISAC settings. So we can see the point-to-point communication, and also we're detecting this target, right? So for the communication receiver, it will receive this YC, which is HC communication channel, multiply X, which is ISAC signal, plus ZC. And here for the sensing receiver, it will receive YS equals to HS multiplied with this X and plus ZS, right? So we should pay particular attention on the difference between HC and HS. Here, in the communication system, we typically just wish to know the CSI. So we just wish to know the elements of this HC matrix, right? We consider this matrix as an unstructured matrix, a CSI matrix. But in the sensing sense, we typically were not interested in this matrix HS itself. What we are interested in is the sensing parameters contained in this HS. So we see that this eta, which is a vector, can be angle, range, velocity, and it is of course some random variable subject to some distribution here. And the other very important aspect is that we are transmitting this ISAC signal X because we wish this X to convey information, right? So it should be a random signal, right? It should be a random signal. So X must also subject to some distribution Px. So here we should pay particular focus also on the two covariance matrices of X. One is the sample covariance matrix, which is XX Hermitian over the time duration t, right? And here, this is a statistical covariance matrix, and which is an expectation of the sample covariance matrix. So we're using this tilde to represent a statistical covariance matrix. And if there's no tilde, that means this is a sample covariance matrix. Okay, so we'll use all these notations throughout our topic, our talk. Okay, so this is our very basic model, vector Gaussian model. And here, ZC and ZS, they're both Gaussian noise. And you can see these models, they are not necessarily MIMO systems. They can also be OFDM systems, okay? So not necessarily MIMO. Okay, and here we have some very important assumptions here. So why is that we're using downlink device-free sensing? So device-free means that the target is non-cooperative, so it does not have a communication device attached to that target. So we're just doing like radar sensing. So this means device-free sensing. And here the dual functional signal X is shared among sensing communication. And of course, because this is the ISAC signal, right? So the signal should be known to the sensing receiver, because in the monostatic sensing case, we have a collocated ISAC transmitter and a sensing receiver. So this X is perfectly known to the sensing receiver, but it is unknown to the communication receiver because it conveys information to the communication receiver. So it should be unknown to receiver, okay? And here we also assume that sensing parameters randomly change every T symbols in an IID manner. So this eta will change every T symbols in an IID manner. And another assumption is that the communication channel also randomly changes every KT symbols. So here K is an integer, okay, also in an IID manner. So in an extreme case, it also changes every T symbols. This corresponds to the case that communication and sensing channels, they may have certain correlation between them, right? So this is about our assumptions here. Okay, so now we should take a look at our today's main role, which is the CRB. And here the CRB is a little bit different from the conventional CRB using in the radar systems. That is because we are using a random signal X to detect the target, right? So that is the specific constraints imposed by the ISAC system, because we needed this X to convey information. And in a conventional radar system, we are not transmitting a random signal to do sensing, right? We just transmit a deterministic signal here. But in ISAC case, we should use random signal to do sensing. So that will cause a little bit of trouble on the formulation of CRB, because now X is random. And what we're interested is to estimate this eta from YS, right? So we observe this YS and we wish to estimate eta under the knowledge of X. And now X is a random variable, then there's different approaches to treat the CRB formulation. So why is that we can treat the X as a nuisance parameter and treat X as part of the an extended parameter, right? So you can treat X also as part of eta, but that will give you very loose bound, right? Because here X is not a parameter to be estimated because it is known to the radar receiver or sensing receiver. Or we can use marginal CRB. So marginal CRB is that we can integrate out X in the likelihood function describing the observations. And this, again, cannot adapt to the case where X is known. And also, this will be very complex, right? Because the integration can be very difficult to calculate. And our choice here is the so-called Miller-Chang CRB, Miller-Chang bound. That is, we compute the CRB for given instance of X and take the expectation over X, right? So that is our choice. And this is actually very typically difficult to be computed, but fortunately, in this vector Gaussian case, it has a very insightful formulation that we will introduce in our later slides. Okay, so this is the CRB, and what we're using to describe the sensing performance bounds. And let's back to the CRB-rate region. So here we will pay particular focus on two corner points on the trade-off curve. One is PCS. So PCS is to optimize the sensing performance when the communication performance is optimal. Okay. So for example, I already achieved my communication capacity. How can I minimize my sensing CRB, right? So this is the PCS point. And at this point, we know that we have a well-known transmit strategy in the Gaussian channel, which is to using Gaussian signaling. So Gaussian distributed signal will achieve the capacity of point-to-point Gaussian channel. So that is the conclusion from the information theory textbook. And there's also another very important counterpoint, which is PSC. So PSC is to optimize the communication performance when the sensing performance is optimal. So when the CRB reaches to the minimum, so how can I maximize my communication rate? Okay, so here the strategy is unknown. Okay, because we didn't know either what is the sensing optimal waveform at this point, and when I have this waveform, how can we optimize the communication performance? Okay, so if I can have these 2 points, if I can characterize these 2 points, then there's a very simple strategy, which is time sharing. This is the line segment linked between PSC and PCS, and that will give you an inner bound of CRB and rate region, right? So inner bound is something that is achievable, that is inside the actual boundary. So actual boundary is here, right? And accordingly, we'll also have outer bound, right? And we will describe the outer bound also in the later slides. Now, let's look at some details of the CRB. And in particular, we should look at the structure of the facial information matrix in this case. So remember that what we are assuming is that we have target parameter changes in IID manner every T symbols. So every T symbol will have a realization of eta, right? We'll have a realization of eta. And because you're transmitting also random signals, so every T symbol you will have a different realization of X, this ISAC signal, right? X1, X2, X3. So every T symbol you will have a different CRB. So because we will have the CRB X1, which is determined by the first realization, and the CRB2 determined by second realization, and the CRB3 determined by the third realization. Because X1, X2, X3, they are realization of a random waveform. So CRB1, CRB2, CRB3, they're all random variables. So in that case, how can I measure the systematic performance of the sensing CRB? So we're using this Miller-Chang type CRB, and we call this a meta CRB. So we simply take expectation of the CRB for a given X, right? So we average over all the X with respect to the distribution of X, and that will give you a universal CRB, which is a Miller-Chang type CRB. And we see the MSE is also a lower bound of the MSE. And if we look at inside this expectation, we're considering the inverse of the facial information matrix of a given X. So this facial information matrix is the Bayesian facial information matrix. It looks like this. So Rx, remember that this is the sample covariance matrix, which is here, right? So it is a fine mapping of the Rx. So what does this look like? So it is this map, this function, so phi A, right? And you can see that for a given A, it has Fi and Gj that multiplied to both left and right-hand sides of A, right? And you have summations for in terms of different Fi and Gj, and also you should plus a JP here. So here, Fi and Gj, they are partitioned from the Jacobi matrix F. So what is a Jacobi matrix? It is actually a derivative of the sensing channel matrix HS with respect to eta, the parameter here. And this Fi and F and Gj, they're simply the partition of this very big, very giant matrix. And the GRP here is contributed by the prior distribution of eta. So we'll have some prior information about eta. Okay, and then we simply calculate the facial information matrix for given x, and then we take expectation over that inverse of the trace of the inverse. Sorry, then we get the Miller-Chang type CRB. Okay, so with that BCRB, that Miller-Chang type CRB, now we can deduce some very interesting iterations here. So deterministic versus random. So for all of us who are doing integrated sensing and communication, we may have some sort of iterations that communication systems, they may desire random signals to carry information. And in the Gaussian channel case, we need to transmit a Gaussian signal, which is the most random signal that carries the the largest amount of information, right? And in contrast, our sensing systems, they desire deterministic signals for estimating parameters, right? We need our signals to be as stable as possible, such that we have a stable sensing performance. But here we have our first lemma, right? So we see that when the sensing optimal statistical covariance matrix is unique. So what does that mean? That this matrix is unique? That means if we're going to minimize this BCRB with the optimization variable R tilde X, then if the solution of this problem is unique, then we see that the sensing optimal signals will have deterministic sample covariance matrix. So what does that mean? So that means our sample covariance matrix is equivalent to the statistical covariance matrix. And remember that they are very different. They have different definitions, right? Sample covariance is like this, and the statistical covariance matrix is the expectation of this. So when we see that this sample covariance matrix is deterministic, that means that they are equal to each other. So how can this Rx be deterministic since X is already a random variable? So how can we do that? So I'll give you some iterations here, okay? And so if we look at the SISO case, so SISO case means that I only have, let's see, one antenna, and the time duration is 1, okay? I only transmit one symbol, so T equals to 1. And in that case, when the sensing, when we have the sensing optimal signal, that means its amplitude should be constant, okay? So that corresponds to this conclusion that the sample covariance matrix should be deterministic. And in the SISO case, that means the amplitude should be constant. And actually, this lemma is derived from the Jason's inequality by noting the convexity of this CRB. Okay, you can see that the inverse, the trace of the inverse of this linear map, affine map of Rx is actually convex function, and you have expectation over that convex function. Then naturally you can use Jason's inequality like this, right? So for any convex function fx, the expectation for fx is larger than or equal to fex, right? And when is the equality attained? So when x equals to ex. So that is why we have this lemma, okay? And let's see, in the SISO case, we will need a sensing optimal signal to have constant amplitude, but in the communication optimal case, we need the signal to be like in Gaussian distributed constellation like this, right? So because only through that we can transmit as much as information as possible. But here, when we have sensing optimal signal, the only degree of freedom here lies in the phase of this signal. So that means we can only use PSK modulation to transmit information in order to achieve the minimum CRB, right? So that is a special case for this lemma 1. Okay. So what does this imply in general? So how about the general case? What if we have multiple antennas, multiple symbols? So what does that mean? So that means if I have sample covariance matrix deterministic, so X deterministic, means that X Hermitian should be deterministic. But someone may ask, so your X is already a random variable, how can X Hermitian be deterministic? So that is possible. Just like I said, here I can just have constant amplitude, but a random phase, right? In that case, I can still have random X, but a deterministic covariance matrix like this. And again, because HC is known, you can assume that it is perfectly estimated. You have perfect CSI for the communication channel. Then this whole matrix GSC should be deterministic. So if you do SVD for HCX like this, so U sigma V, and you can see that this V matrix vanishes when they multiply with each other, right? So that means the only remaining degrees of freedom lies in the red signal vectors here, because U and sigma are both deterministic, and the only random variable should be this V matrix. So only the random variable will convey information. Then what we need to do in this case is to using this unitary matrix V to convey information. So that gives us interesting. How do we design the semi-unitary matrix codebook for maximizing the communication rate? So now I can only use this structured symbols, structured codebook to convey information. So that corresponds to something called a sphere packing problem on the Stifel manifold. A Stifel manifold. So the Stifel manifold is the site of all M by T semi-unitary matrix like this. So Q Hermitian equals to I, right? So this is a manifold, which is a curved space, which is not a linear space. And we know that for Gaussian channel, the capacity is attained by sphere packing in the Euclidean space. So sphere packing means that I can insert, many spheres into a given spaces, right? Like this. So the radius of these spheres is determined by the noise variance, right? So it turns out that the uniform distribution over the side of all M by T semi-unitary matrices will achieve the communication capacity, or in other words, it can insert the largest number of spheres into this given space without overlapped with each other, right? So how can we do uniform distribution over the side of semi-unitary matrix? We can simply sample a matrix from the standard complex Gaussian distribution, and then we do LQ decomposition for this matrix to obtain the Q, and then we left multiply Q by some precoding matrix. Then we can have this sensing optimal the sensing optimal constellation, which is consisted by the semi-unitary matrix codebook. Okay, so with that strategy, we can achieve the capacity of PSC point. So remember what is a PSC? PSC is here, right? So it is the maximum capacity that I can achieve under the constraints that I reach the minimum CRB, right? So it's like this. So here we have some discussions. What does the PSC achieving strategy imply in general? So we have this is a high-SNR ergodic achievable rate of this point, right? So you can see that compared to the conventional Gaussian capacity, we have some penalty term here, right? So for Gaussian capacity, we do not have this penalty term. And here, why we have this penalty term? Because we have this Q matrix, it is structured. It is a semi-unitary matrix, and this is the information carrier. So that will give us some insights here. First of all, the signals with deterministic sample covariance will incur performance loss for communication compared to the case with Gaussian signaling. And the maximum communication degrees of freedom loss will be here, the M square over 2T. So because we will also, if we're going to compute the degrees of freedom, we'll also have an MSC multiplied here. And when t goes to infinity, you can see that the communication performance will become lossless, because even a Gaussian signal matrix X would have asymptotically orthogonal rows for t goes to infinity, right? So it's like this. So these are some discussions on the point of PSC. And now we look at another point, which is PCS. So PCS, we know that this is a point that when the communication rate achieves the optimum, and I trying to minimize the CRB here. So for communication, we know that the optimality of Gaussian signaling is well known, and this is the Gaussian signaling achieve the capacity here, right? Like this. So what if I'm using a Gaussian signal for sensing? I think that is a problem that has not been well investigated before. So we can see that if I'm using Gaussian signal for sensing, then we'll have certain performance loss compared to deterministic signals. So here, this is a CRB. This is our CRB, and we have a lower bound and an upper bound for the CRB. So why we have these two bounds? So we can see that actually, let's first look at the communication optimal waveform structure, which is when I have an optimal covariance matrix. This is a statistical covariance matrix. I should transmit, Gaussian signal on the subspace of this covariance matrix, right? So like this. So this is the communication optimal waveform, something like this. And here D contains IID Gaussian entries. And we have an upper bound, which is like this, and lower bound like this. So why we have this lower bound? Because again, we can use the Gaussian inequality, right? Because inside the expectation, we have a convex function. So we can use Gaussian inequality here. And here, this one is a non-trivial upper bound. You can see that this part is equivalent to a lower bound, but with a scaling factor t over t minus mean K rank R tilde X, right? So that will give us some observation here. So first of all, again, the Gaussian signal will incur performance loss for sensing compared to the case with deterministic sample covariance matrix. So what is the case for deterministic covariance matrix? It is something like this. And we'll certainly have performance loss because this is a lower bound. And the maximum DOF loss will be the minimum of K or rank R tilde X, right? So this rank R tilde X will be actually when we have high SNR. This R tilde X is obtained by the auto failing, right? So everyone knows that we're using auto failing to maximize this communication rate. And when you have high SNR, then the rank of Ix will be equal to the rank of HC. So this will be a penalty term, right? And again, when t goes to infinity, the sensing performance is lossless since the sample covariance becomes deterministic for t goes to infinity due to the law of large numbers, right? And here we should pay particular focus on this upper bound because it is said that if I have a very small number of parameters to be estimated, let's see, in the extreme case, we have k equals to 1, then you can see the performance loss will be upper bounded by t over t minus 1, so which will be very small. That means if you have a sufficiently large sensing period of t and you have very nice sensing parameter, then you can safely use Gaussian signal, right, without too much performance loss. Okay, so we have some summary here. So we have sensing and communication trade-off as a twofold trade-off, and we should look at the structure of the communication optimal signal and the sensing optimal signal. So communication optimal signal is obtained by water failing. So here UC is aligned to the communication subspace, and the lambda C is determined by water failing, and the D is IID white Gaussian, right? And here we have US, which should be aligned to the sensing subspace, and the lambda S is obtained by solving this BCRB optimization problem, right? Like this. And this Q should be some semi-unitary, some random semi-unitary matrix, right? So you can see, you compare to these two structures, we can see that when we move from the communication optimal to sensing optimal, two things occur. One is the deterministic random trade-off. So that means the randomness of ISAC signal reduces from the communication optimal to sensing optimal. And in the extreme case, it from a Gaussian signal constellation to the PSK. And the other trade-off is the subspace trade-off. That means the signal power would move from the communication subspace to the sensing subspace. So that is determined by this US and UC, right? And the DRT, deterministic random trade-off, is determined by this Q and D. So that is sensing and communication trade-off as a twofold trade-off. And how can we adjust these two trade-offs? So to adjust the subspace trade-off, we have this approach, which we call a statistic covariance shaping. So that will give you an outer bound, right? So you can simply let t goes to infinity and solve this Pareto optimal optimization problem, which is to minimize the sensing CRB and also maximize the communication rate, because we have a negative sign here. And if you increase this alpha from 0 to 1, you can see that you will move from the sensing optimal to the communication optimal. So you can see that this will form an outer bound by omitting the deterministic random trade-off, because we let t goes to infinity. And how can we adjust this deterministic random trade-off? How can I change the randomness of a signal? How can I change the randomness degree in the signal? So the general approach for adjusting this trade-off remains unknown, because it will be determined by very complicated functional optimization problem, but we may attain various inner bounds by different approaches. For example, we can have time sharing, which is this line segment between PSC and PCS. And we can transmit either Gaussian signal or semi-unitary signal over the S&C sensing communication subspaces. And that will give you these two inner bounds. And we can also have the time sharing between the points of on this 2-point inner bounds, right? Because the time sharing will attend the convex Hall of the CRB-rate regions of any two strategies. You can see that with that strategy, you can have a better inner bound compared to this line segment, right? But this is obviously an inner bound, because it is not, we cannot approve that this is the actual boundary. And here we have some case study, and so we have this very well-known sensing channel model for MIMO radar, and we're trying to sense the target of of angle and its reflection coefficient alpha. And you can see that under this case, the communication dual F loss will be very small. So there will be only one dual F loss. And there will be only one also the dual F loss for sensing if you're transmitting the Gaussian signal. And that will give you different bounds. So again, this is the inner bounds line segment linked to 2 points, and the Gaussian signaling inner bound and semi-unitary inner bound. And also this is the convex Hall or time sharing between these 2 inner bounds, and there's an outer bound, right? So you can also look at the subspace correlation results in this case. And you can see that by increasing the correlation coefficient from 0.05 to 0.99, we get better and better trade-off for both inner and outer bounds. So here, this green line is the inner bound and blue line is outer bound. And for the deterministic random trade-off, we can try to increase the time duration t. You can see that if I'm increasing this t, I can get narrow and narrow gaps between this inner and outer bounds. That means the deterministic random trade-off will become less prominent when we have a larger t. Okay, so I still have I think several slides for our recent new work. So I would like to ask a question here that is deterministic random trade-off universal? So by universal, I mean, is this trade-off a universal trade-off for arbitrary sensing metrics, or it is effective only for the CRB, right? Because you can see that we consider we have different sensing metrics here. We have PD, PFA, mean squared error, camera bound, right? So can we use different performance metrics? So will this DRT still hold for different performance metrics? So that is a very fundamental question. And again, to answer that question, we should look at another performance metric for sensing, which is a mutual information. So let's recall the sensing signal model in ISAC system. We have YS equals to HS eta X plus noise. And here X is some random variable, and eta, the parameter, is some random variable, okay? So the sensing mutual information is the mutual information between eta, your parameter, and the YS, conditional on the X, on this random variable. So we actually have this identity. That means the mutual information between eta and YS is equal to that between HS and YS. That is because HS is a deterministic function of eta. Okay, so you can prove that in a very straightforward way. And normally there's no closed form for mutual information unless this HS is Gaussian distributed. But fortunately, we have some property for this mutual information. That is, no matter what kind of distribution is for this HS or for this eta, we know that the sensing mutual information is a concave function. So when we have X, we have some realization of XA, then we see that this mutual information is a concave function on RA, so sample conversion matrix of RA, okay? So this is a very useful lemma here. And with that lemma, we can again have a deterministic random trade-off phenomenon in the sensing mutual information, because now this I eta RA is a concave function. So I eta RA is this one, okay? So now this is a concave function. Then you can again use Jason's inequality to apply to that concave function, and then that will give you this proposition that when the maximum is reached, then this Rx will have deterministic trace. In particular, if this problem has a unique solution, then X itself is deterministic, and it is equivalent to the statistical covariance matrix. And the proof is very straightforward by using lemma 4, okay, by this lemma and the Jason's inequality. So we see that again, the deterministic random trade-off exists also in the sensing mutual information, okay? So with the sensing mutual information, we can consider the distortion matrix for sensing. So they have very close connections. So what is a distortion matrix? A metric for sensing. So most sensing performance metrics can be induced from a distortion function. So some distance between the ground truth and its estimate eta hat, right? For example, MSE can be induced from the Euclidean distance between eta and eta hat, like this. And the PD, the detection probability, this can be a little bit non-trivial, but we can see that this can be induced from the Hamming distance. So Hamming distance is something like this by considering eta as 0 or 1, so an indicator to indicate whether the target exists or not. So in this case, the expectation of this Hamming distance is equivalent to 1 minus PD plus PFA. So that is under the Neyman-Pearson criterion. So if we have a fixed PFA, then if we minimize this Hamming distortion, the expectation Hamming distortion, that is equivalent to maximize the detection probability, right? So you can see that many typical sensing metrics are essentially distortion metrics. So here we consider rate distortion of eta. So rate distortion theory is invented by Shannon. So we have the rate distortion function of eta, which is to measure the mutual information between eta and eta hat, subject to that the distortion, average distortion of eta hat should be less than D, right? So this is RD. So that means so the minimum bits that I can use to quantize eta under a given distortion D. So this is the rate distortion function. And we'll also have distortion rate function, which is essentially the inverse function of RD. And this RD is monotonically decreasing in D. And it is also the DR, this distortion rate function, is inverse of RD, okay? So these are some basic knowledge of rate distortion theory. And with that, we are ready to have our next theorem, which is the distortion lower bound. So that means for any estimate eta hat of eta, right? And some distortion function. So either can be Euclidean distortion or Hamming distortion or other kind of distance function corresponding to different sensor metrics. So you can see that given this D, then the average distortion of recovering eta from the noisy observation YS is lower bounded by this distortion rate function. And here the distortion rate function should be bounded by this one, okay, this I eta R tilde X. So when is this equality attained? So in particular, if the solution of the MI maximization problem, this problem is unique, then we achieve the equality, okay? We achieve the equality of B, and the X itself should be deterministic. And this theorem can be proved by simply applying the data processing equality to this Markov chain. So you can see that eta HS to YS, X, and to eta hat, this forms a Markov chain. And if we apply the data processing equality, we can get this distortion lower bound. And here we have some discussion about these results. One is, again, we have deterministic random trade-off in ISAC system. And now this trade-off is universal because in this theorem, we do not specify the distortion function that we use. So this can be MSE, can be PD, can be CRB, so any kind of sensor metrics. So which implies that this DRT may hold for a variety of sensor metrics in addition to CRB, okay? And the other very interesting insight is that we can regard wireless sensing as a non-cooperative source channel coding process. So why is that? Because if we look at this physical procedure that the ISAC transmitter transmits X, a signal to sensor target, and then it will be reflected back to the sensing receiver. So the reflection will be YS. So if we look at YS from the radar sensing perspective, we see that eta, they are target parameters, and they form a sensing channel matrix HS. And here X is an ISAC signal, so it is random signal, okay? And YS is the observation at the sensing receiver. And from that observation, we need to estimate a target parameter from YS. So that is from the radar sensing perspective. So how about we look at this procedure from information theoretical perspective? So we can regard this target, okay, as a non-cooperative source that wish to communicate the information of eta to the ISAC receiver. And in that case, you can see that eta is the source, okay? It is a source subject to some random distribution. And HS eta, this becomes a channel input. And what is the channel matrix here? So the channel matrix is actually X, but now this is a random channel because we should transmit a random ISAC signal. So you can regard the signal as a channel, right? In this case, and this is essentially the duality between signal and systems. And the YS is output of this channel. And then we need to estimate a source from that channel output. So you can see that essentially this procedure is as if that I have a source here and it encodes eta into a channel input. And this encoding procedure is exactly a source channel coding procedure, right? So that is why we have this separation lower bound here, because this lower bound is actually very similar to the converse of the source channel separation theorem in the Shannon theory, okay? So this is another very interesting insight from that theorem. Okay, finally, I would like to reach to the conclusion of our today's talk. So remember that we have talked about the flashlight analog or the torch analog for ISAC. So we're trying to steer my torch to either the communication direction or the sensing direction. But now we have a full picture of this torch analog. So the ISAC system, it is not just a torch. So it is actually a projector, okay? So we wish to simultaneously illuminate a target, so that is sensing, and transmit an image, so that is communication, using this projector. And the brightness of each pixel of the transmitted image will convey information, but those dark pixels will result in imperfect illumination. So this will result in the performance loss in sensing, okay? So that is why we have this deterministic random trade-off, because we wish to transmit image, so we need random pixels, so either dark or bright pixels, then they are randomly distributed, but those dark pixels will result in performance loss. And that is a full picture of the torch analog. Okay, so if you are interested in our work, you're more than welcome to check these 2 papers on arXiv. Okay, so that's all for my talk, and I'm now open for questions.
Okay, thanks, Fan, for the very interesting talk. And we got several questions. So the first question is from Professor Hajid Messer. So Professor Hajid, could you please open the microphone and ask the question by yourself?
Yes, thank you. Do you hear me?
Yeah, we can hear you.
Okay, hello everyone. A wonderful talk. Thank you very much. It was really inspiring. And I appreciate very much your approach of optimizing the gain in terms of sensing and communication. But my question regarding a third component which is missing, I think that the ISAC is very important also for sustainability, because having less equipment and less pollution is also important. So I wonder if you can add also to your gain consideration a component measuring the ISAC contribution to sustainability.
Many thanks. So that is a good question, because actually in this description of our measurement of the ISAC gain, we have already incorporated this sustainability perspective, because here, if you have higher gain in ISAC performance, that means you will have higher efficiency in using the wireless resources, right? So for example, if I wish to achieve, a better communication sensing performance, that means we will always need to, have more power consumptions, or we need more bandwidth for given, preset localization accuracy or communication rate. But now, if I combine them together, I can use, for example, the same bandwidth or the same power to reach our previously, given localization accuracy or communication rate, and that means I improve my resource efficiency, and I'm using less power consumption, less bandwidth to reach to a given, performance requirement. So I think that will contribute to the sustainability perspective. I hope that answers your question.
Actually, I was meaning more like physical equipment, like if you take footprints over the ground, if you need more technology. So this is something which is not respected by your measurements, I think. And I wonder if it can be added.
That would be a little bit different, because for those components, that is mainly about the hardware platform. And here, what we are referring to is actually the wireless resources. So we are considering the efficient usage of the wireless resources and not the hardware. But just like I said, if I can efficiently use the wireless resources for both communication and sensing, then I can certainly consume less power, and then I can certainly, has less restrictive requirement for my hardware platform, and that will give you some performance gain in the components. But that is not quite straightforward. But I think that is something that we should consider in the hardware perspective, not in the wireless resources perspective. Yeah.
Thank you. Very clear. Thank you.
Okay, so we also got some other questions from Ahmed from NYU Abu Dhabi. So Ahmed, can you open your microphone?
Yes, thank you, Jay, and thank you, Professor Liu, for the very interesting talk. I'm from NYU Abu Dhabi, and I also work on ISAC. So I have a couple of questions, more like technical questions, like, so you consider a lot I've read one of your archive papers on the integration gain, and you showed an illustration about when the sensing and communication subspaces are highly correlated, that's when we get the integration gain. And when they're orthogonal, there is no gain. So my question is, according to one of your theorems on the optimal waveform structure, where you load the steering matrix, its derivative, and the left singular eigenvectors or singular vectors of the communication subspace, that's the optimal way of doing the waveform. My question is, do we know the sensing parameters beforehand? Because that's the only way to form that waveform, right?
Yeah. So you raise a very good question here. So if I understand it correctly, you're asking whether we know the ground truth of the parameter, right?
Yes, exactly.
Yeah. So we do not need to know the ground truth, because here we are considering this Bayesian CRB. So Bayesian CRB means that we only need to know the prior distribution P eta here. And when we formulated the facial information matrix, we will have an expectation here. And this expectation is over the distribution of eta. So in that case, we do not need to know the ground truth. So that is an advantage of using Bayesian facial information matrix. Yeah.
Yes, thank you. But the optimal waveform is a function of the
distribution. Sorry, it is
of the true sensing parameters. According to theorem 1 of the archive paper.
No, it is not the function of the parameter. It is the function of this distribution.
Okay.
So here we only need the distribution to calculate the BCRB in this optimization problem. So in the objective function, there will be no ground truth parameter in the objective function. Yeah. So we only need to know the distribution. So that is what we need to know. Yeah,
that's very interesting, because so I think I missed the Bayesian point of the things, which is very interesting. And the other thing is, on slide 33, you mentioned that X is random, the ISAC signal is random, but it's the base station that generated that signal. Why do you assume it to be random?
Because it needs to convey information. Because in the information theory, only random signals carry information.
I see.
Yeah. Right.
Okay. Thank you. Thank you very much.
Okay, thank you for a nice question.
Okay, thanks. We also got another question from Lin Nong Wu. So Lin Nong, could you please open your microphone and ask a question yourself?
Okay, can you hear me?
Oh, yes.
Yes, I can hear. Yeah.
Okay. Thank you for this very inspiring talk. Actually, based on my understanding, I say you presented this deterministic and random trade-off. So to me, if you have this, let's say, you presented the PCS and the PSC, these two standing point on this parallel boundary, and for each of them, you can derive the optimal signal structure, right? And so based on these 2 points, you can draw a boundary, maybe not a parallel, but you can still draw a boundary on this on the plane. And then one question is, okay, if we have this, we know this structure, and then will it give us a new design perspective on how to design this dual function waveform, or how to compare it with the existing, let's say, optimization approach. Because now there are many works. We have the sensing-centric or communication-centric, and then we write the communication throughput as a constraint or as an objective function. So how do you compare these, your results, and then how can we use this result or insight to improve the current design approach?
Yeah, thank you, Lin Long. That is a very good question. In terms of the existing optimization-based work, you can see that they actually have some implicit assumption in their system setting. That is, we are always transmitting Gaussian signals, right? Because in many ISAC optimization papers, if you're optimizing, let's see, the communication rate, you're actually using the Gaussian capacity, something like this, right? And if you're using that, that means you're always transmitting Gaussian signals, right? And that assumption is actually not optimal, right? According to our analysis here. And you can see that for the sensing optimal case, we should not transmit Gaussian signal. We should transmit the semi-unitary, random semi-unitary matrix like this, not a Gaussian matrix. So that will give you a very different, very different high capacity expression like this. Right? You can see that I have some penalty here because I'm not using Gaussian signals. I'm using this, semi-unitary matrix. So that will give you essentially very different formulations in your optimization problems. And also, like I said, if we look at existing optimizations, most of them are actually considering the outer bound of the actual boundary, because they assuming explicitly the Gaussian signaling, right? And in that case, that is equivalent to let t goes to infinity. So that means we do not differentiate between the sample covariance matrix and the statistical covariance matrix, right? So in many of our previous works, we simply treat them as a single covariance matrix. But now you can see that that assumption only holds when t is sufficiently large. So in that case, we can do our usual optimization like this. So I minimize the CRB, maximize the communication rate. We got a Pareto optimal boundary, but that is under the assumption that these two metrics, they are equal to each other. But in the more, information theoretical sense, or in a more practical sense, these two matrices were never equal to each other, only because this t is finite in our actual ISAC system, right? So they were not, equal to each other. Then they will result in different formulations again in the CRB and also in the rate, and that will give you a very different boundary, which is here the actual boundary. So all our optimization is to consider optimizing this boundary, this outer bound, but the actual boundary lies here. Okay, so that is why we should consider the distribution of the transmitted signal. So essentially, this optimization problem to get actual boundary should be a functional optimization, because now your optimization variable is not x, but the distribution of x, right? So that will give you a very complex optimization problem that your current approach cannot handle that. We need some more advanced mathematical tool to solve that problem.
Yes, thank you very much. Actually, I think your results is very inspiring. It will help, from my side, will help me to shape this optimization formulation into a very profound way or to the next level. Thank you very much for your answer.
Thank you very much, Lin Long, for your nice words.
Okay, thanks. And we also got a question from Zelan Zhang. So I will ask a question on his behalf. So Fan, on your slide, okay, page 13 or 14, you mentioned that the CRB is loose when we consider x as a parameter, which needs to be estimated. So the question is why the CRB is loose in that case.
Because in the ISAC system setting, X is already a known waveform, although it is random, but for the sensing receiver, it is perfectly known because this is the signal that's transmitted from the ISAC transmitter, and the ISAC transmitter can be collocated with the sensing receiver. So the prior information about X is perfectly known. So if that X is perfectly known and you assume that you treat this as an unknown parameter to be estimated, then you will certainly get a loose bound. So that is why we will get a loose bound.
Okay, thanks. So let's move to the next question. So we got another question from Harrison Fang. Harrison, can you open your microphone and ask a question by yourself?
Sure. Can you hear me?
Yes.
Yes.
Thank you for the nice talk, by the way. I have a few questions. Number one, to obtain your results regarding the DRT and the subspace alignment, you optimize the sensing metric while maintaining a certain communication QoS. I was wondering if you will be able to get the same result if you were to reverse the problem, so to speak, when you try to optimize the communication metric while maintaining certain sensing quality.
Yes. So technically, these two problems, optimizing sensing metric subject to communication metric performance, and optimizing communication performance subject to sensing performance, they are technically the same actually, because when you do the true optimization, you will get the same Pareto boundary, like here. So you can see I have this minimization CRB subject to rate, right? And if you change their
Actually,
position,
I cannot see your screen. Can you share it?
I think okay. So let me. Okay. So if we look at this problem, if I minimize the CRB subject to rate, communication rate, and or if I maximize the communication rate subject to CRB, that will essentially give you the same boundary. So the results will be the same because this Pareto optimal boundary will be the unique boundary for these two performance metrics. Okay, so you can also obtain that boundary by weighted optimization. For example, you minimize alpha multiplied with CRB minus 1 minus alpha multiplied with rate, and you change that alpha, you will also get this boundary. So you have different ways to get that boundary. The results will all be the same.
My second question is on page 22. You mentioned that you get a greater DRT trade-off by using more time slots. So that might not be a problem for sensing, I think, but it's a serious problem for communications because it reduces the communication bandwidth. So I was wondering if you're forced to use, say, OFDM, because this is what the waveform that we're using for communication right now. Do you have any insight as to what would happen if you were to use OFDM? Would that add to the additional bandwidth loss?
I think the bandwidth loss. So actually here, the time duration will be a problem in the, I think in some very specific practical scenarios like IoT or URLC that you will use short packet for communication. And in that case, this time duration will matter, right? But in OFDM, you actually have very long block length in the OFDM. And you can see that under this system setting, when I have 50 symbols in this block, then this DRT will become less prominent. So that means that there will be no trade-off between deterministic and random when you have a sufficiently large time duration. But if you have short duration, then there will be a trade-off. So that does not mean that I should use shorter duration for sensing or communication. That all depends on your scenarios. So whether you are, for example, you're transmitting short packets in the IoT network in your ILLC scenario, or you are transmitting, conventional signal blocks. In, for example, OFDM, you may have very long signal blocks and sufficiently large T. And in that case, there might be very, weak trade-off between deterministic and random, and that will not be a problem. Okay.
Are you saying that for OFDM, you can actually exploit the frequency domain as well? So that's why you don't have to care about this T when you're using OFDM?
Yes, because this T is not necessarily for the, let's see, the time. It can also be in the frequency. So this T is actually, technically speaking, this is the number of independent samples in your observation. So this samples can be on the frequency domain or on the time domain.
Okay, great. Thank you.
Yeah.
Okay, so Fan, please, I just missed one question. So maybe this will be the last one. So so I think Terry Guo asked a question related to the integration gain. So Terry, so could you please open your microphone and ask a question?
Sure. Thank you for your talking. It's great work. People talking about integration gain. Of course, that's, I don't know the relation between the gain and your work.
Okay, so thanks, Terry. Actually, all this description of ISAC gain is related to the integration gain, because the integration means that how can you more efficiently reuse your signal resources like power and bandwidth between communication and sensing, right? So why we have gain ISAC system over those individual communication sensing systems? Because we can reuse resources between two systems. We do not need to orthogonally allocate resources between them. And with that resource reusing, you can certainly achieve the performance gain. So that is the so-called integration gain. Because if we look at, so this is a very simple illustration here. And for those, let's see, the individual radar and communication system, for example, they are doing time sharing, they're doing bandwidth sharing, or beam sharing. So then you can see we may obtain some performance bound like this, right? So this is obtained by time sharing. But if you can reuse the time resources, we're using the same signal for both sensor and communication, then we have some performance boundary like this. And if you compare these two boundaries, you see that this will definitely achieve, performance gain compared to, conventional radar and communication system. So that is exactly the integration gain here.
Yeah, I agree with you. I just wondering, is there any a mathematical way to define the integration gain?
To be honest, I think that one is that is also a very interesting problem that we're currently investigating in our lab. But I think that is actually very difficult, because a very simple way to measure that again can be considered as the covered area of this boundary. You can see that. So if you have a larger area, you have larger performance gain, right?
Yeah.
But but sometimes these curves can be crossover with each other, and in that case, the measurement using that area might not be accurate. So that is also a open problem, I think. Yeah.
Yeah, good answer. Can I ask another question? Very small question.
Okay, please.
Yeah. So you consider the I guess you consider interference, I mean noise, as a Gaussian noise, but in the sensing case, the clutter is not a Gaussian. So maybe that's your future work.
Yeah, I think that will be our future work, because like I said, here we consider this vector Gaussian channel. So that is a information theoretical scenario that you only can see the Gaussian noise here. But with clutter, the things will definitely becomes very different, because the clutter will have a different distribution, right? And for that distribution, you need to compute all this, CRB and communication rate in a very different way, and even with no closed form solution, and very difficult to analyze. So I think we start from the Gaussian case, and we may consider other more complicated cases in the future.
Thank you very much. Have a good weekend.
Yeah, thank you very much.
Okay, thank you very much, and thanks, Fan, for the wonderful talk and the insightful answers. So I think, yeah, time's up. So maybe we should stop here. Thanks all for attending this talk. Yeah.
Okay, thank you.
Thank you very much, and see you next time.
See
Bye-bye.
you. Bye.